Assalamu alaikum. Welcome to Turkish Engineering. In this lecture, we are going to solve a thermodynamic cycle problem. So this is an air standard cycle with variable specific heats. Please focus on this term. If question mentions variable specific heats, we know that Cp and Cv can be approximated to 1.004, 1.005, will be like in this range. If we are working with to room temperature and what's like around the room temperature, and we don't have high temperature range. But if we go to like higher than 500 kelvins, or like we are reaching to 1000, there will be a huge temperature change. And we know that Cp is a function of temperature, but that not that much sensitive. You see that it's not changing like enormously, but if you have a high temperature range, you cannot treat Cp or Cv as constant values. So this is what like question meaning, and we will alternatively, instead of using specific heats, we should find another way, which is like following air tables. Okay, we will go to a 17 air standard like air ideal gas properties of air is carbon dioxide. This is nitrogen. This is air. Okay, so here you only need information of temperature to find other properties. Okay, so let's start filling our table here. Okay, we have a closed system, mass is constant. So at the beginning, isentropic compression from like 1 to 2. This is the first process. Isentropic compression means S1 and S2, they're equal to each other. I can set any reference value. The entropy change is important, but entropy value is not important. We are interested in delta S, because you realize in some thermodynamic tables, you find a entropy value, let's say 2.1. You go to another table, you find 1.8. Why? They have the same state but different entropy values, because tables are based on different datum or reference points. What is important is just the entropy change, not entropy itself. So here, just fit to 0 and just simplify it. Okay, we are interested in delta S. Okay, then isentropic compression from 100 kilopascal. Let's put 100 here, and 22 degrees of Celsius will be equal to 295 Kelvin, and we have the second pressure here. Okay, then constant volume heat addition to 1500 kelvins for state 3, and we have constant volume. That means like this V3 will be equal to V2. When I find this, I will also insert that value here. It is isentropic expansion to 100 kilopascal. So I understood that we are going back to same pressure. 4 and 1, we have the same pressure, and okay. So it's isentropic expansion. So that means S4 is equal to S3. But I don't know S3. Actually, there is an entropy change between 2 and 3. I must calculate this. I don't know now. I will calculate and find this value. Then this value will be equal to S4 also. And P is equals to constant when you have heat rejection to initial state. Okay, from 4 to 1, you have like a heat rejection, but pressure is constant. That means there is a work. Okay, there is a work. So let's put some other information for the processes. We can just directly insert them. For example, isentropic means Q is 0. Okay, so from 1 to 2, Q is equal to 0. I know from isentropic, because isentropic means adiabatic and reversible. Okay, so adiabatic, no heat transfer. Here, constant volume heat addition. Constant volume means W is equal to P delta V if P is constant, or let's say like integration of P delta V. dV is like there is no change in volume. That means this is 0. Okay, there is no work from 2 to 3. Okay, I will use them when I use the first law of thermodynamics. Isentropic expansion. Okay, Q is equal to 0 again from 3 to 4, and here I have Q 4 to 1 minus W 4 to 1 is equal to delta U 4 to 1. I have like non-zero values of work, because I have constant pressure, volume is changing. So that means I cannot say neither Q is equal to 0 or volume is equal to 0. There will be some values for them. Okay, as a first step, I will start by the isentropic compression process, okay? The first process, isentropic compression. For the isentropic process here, I will follow the air ideal gas properties table. So here, our first temperature is 295. Let's take these values here. Let's only filter our region of interest. Take this here. Okay. So what we can do is just inserting U values for this one. And we can calculate the specific volume from the ideal gas law. Okay. So let's plug in all values. Then 100 kilopascal. You will get 0.85 meter cube per kilogram. Okay. So I'm using red color for the calculated parameters, and the others are givens. Okay. So second step, how do I know? Okay, I will use tables and a property that is related to temperature, which is critical pressure. Okay. So I know critical pressure at 1, and critical pressure ratios for this isentropic process will be equal to pressure ratios between these two steps, okay? So PR2 over PR1 is equal to P2 over P1. This is how you work with variable specific heats. You don't use specific heats, you use critical pressure ratios, okay? So from there, you will say PR2 is equal to PR1 over times 6, which is the pressure ratios. This is 6, I know from here. Okay, 600 over, let's say 600 over 100. Then PR1 is from the table, is 1.3068 times 6. That will be equal to 7.84. Okay, so I will now I have PR2. I will go to table to like search this value corresponds to each temperature, so I can calculate the temperature from there. Okay, so let's see here, PR is changing by increasing temperature, and I will okay, I found it here. I have 7.82, which is close to our value. We can like simplify it and don't make any interpolation for now, because it's very close to this. Maybe 1 or 2 degrees will affect on if I make interpolation, so it doesn't matter too much. Okay, I will say that my second temperature from here, T2 is equal to 490, and I can also get U or S values from here when I need. Okay, just fill the table now. When I need, I can go back because I already copied them here. So U is equal to 352.1, let's say. And what about V? Here, I can calculate V from ideal gas law easily, right? V2 is just RT2 over P2. T2 is 490 over pressure, okay? It's meter cube per kilogram. Okay, so let's use red color for the calculated values again. Okay, completely done. We know the process from 1 to 2. And now we can also use the ideal gas, the first law of thermodynamics. Q from 1 to 2 minus work from 1 to 2 is equal to delta U, or you can say U2 minus U1. And I know it's isentropic process, so Q is equal to 0, right? So I can find the work, right? Work from 1 to 2, if you send this negative sign to other side, U1 minus U2, which is equal to so here negative work I have, right? Negative work means the work done on the system, okay? kilojoule per kilogram. This is the first work, okay? But just leave it here. I will, when I need to find a network or other parameters, I will come back and collect these values. But for now, just we need to go through the other processes. From 2 to 3, what I know. Okay, volume is constant, perfect, because I know specific volume at 2, so that will be equal to this specific volume again. And from there, we can find P, right, from the ideal gas law. So P3 is equal to RT3 over specific volume 3. Okay, so this one, then T3, what's T3? 1000, okay, 1500 over the specific volume, okay? So that will give you actually 180, okay, 1840, I can say 1840 kilopascal. And also insert to table. And what about this one? It's related to temperature. So let's go to table and find it. This one. Okay. I have one, or let's say, okay, 1205. Point what? 4. S, okay, how can I find S? That's good, because we have a non-isentropic process now. I must calculate delta S from 2 to 3, okay? That will be equal to Cp ln temperature ratio minus R ln pressure ratio. But I have a problem here, that this Cp value is changing by temperature, and it's variable specific heat. For high temperature range, I cannot use it. As the question already mentioned, you don't use specific heat as a constant value. So I will just change this to something else, which is known from table. That Cp ln temperature ratios is equal to S naught values. Okay, these S naught values, not entropy values, but they refer to entropy change with respect to temperature. Okay, so these values refer to entropy change corresponding to temperature range, temperature change. So this can be replaced, and now we don't have any specific heat, and R is constant, right? So that we can use this one. S3 is just 3.44 from table, and S2 is this one, 2. Let's say, okay, 20 minus R ln pressure ratio, which is this value, okay? R, which is 0.287 times ln over 600 equals to 0.92, and kilojoule per kilogram Kelvin, right? So let's insert it there. Since the initial entropy was 0, like I set it to 0, so this will be just increasing by 0.92. So I found it, 0.92, and this one is also equal to 0.92, okay? Yeah, so I have last process now, and before it, let's calculate work and Q values here. Work is equal to U3 minus U2. Okay, what about Q? Q is from 2 to 3. We have heat transfer, but work, we have like 0 amount of work because we have constant volume. Constant volume is like, let's say, P delta V for work. If we have constant pressure, we can just use this formula, or we can integrate it. But here, delta V is constant, so no volume change. That means this is 0, right? So this will be equal to 0. So Q from 2 to 3 just equal to internal energy change, specific internal energy change. U2 is just this value, right? 352.1. Okay. That will be equal to 853.3 kilojoule per Kelvin. This is the, let's say, heat input, right? We have heat addition, so this is the heat input. It's positive. If that was negative, that means heat is being released, but this is heat addition. So now the last process, 3 to 4. Okay, 3 to 4, I have isentropic expansion. Okay, isentropic expansion. So I know the pressure ratios. So from the pressure ratios, PR4 over PR3 is equal to P4 over P3. You can get PR4, okay, easily. Let's use this X over PR3. We know PR3 from here. It's 601.9. It's easy algebraic equation, but I like always using this to like be fast at calculator solving any type of equations. And you have P4, which is 100. Then this one is 1,800 left. Okay, this one. So you should just say shift solve. That will give you the answer. So to 32.7, right? 7. From here, I will go to the table and search for this value. 30. Okay, I found it. This one. Again, I don't use any interpolation. I simplify. Okay, I simplify it. So temperature is equal to 720, and U4 is something. Okay, let's insert the values here. 720. You have U as this one is U, right? Third. Okay, third. 528.1. Then you have volume here. The volume can be calculated from the ideal gas law. Specific volume at 4 is equal to RT4 over P4. Okay. Let's find it. The last temperature is 720 over 100 kilopascals. Okay. So 2.06 meter cube per kilogram. We found the specific volume. We completed the whole table. Now we don't have anything missing, only just the first law equation for here. So Q from 3 to 4 minus work 3 to 4 is equal to U4 minus U3. So we have, just remember again, it's isentropic expansion means, isentropic means adiabatic and reversible. And adiabatic means no heat transfer. Okay, so when you see isentropic, just cross on the Q value. So you can calculate the work here. So work value from 3 to 4 is just U3 minus U4. Let's see how to find it. U3. Here I get positive value because the system is doing the work, right? System is doing the work. Okay, I have from 4 to 1. I know all the values. I only just need the heat transfer and work values, U1 minus U4, okay? And this is constant pressure heat rejection. So I must include the work, and I cannot say it's 0. So let's calculate the work. It's just P delta V, because P is constant, right? P4 times delta V. But it will be specific volume because we are calculating specific work per unit mass, right? So it is any one for constant pressure is constant, so 4 to 1. So 100 kilopascals multiplied by the volume change, okay? 2.06 minus 0.85 meter cube per kilogram. Kilopascal times meter cube will give you kilojoule over kilogram. Okay, here you have kilogram. So these two kilojoule, then over kilogram will give you kilojoule per kilogram. So 121 kilojoule per kilogram. And what about Q? Is you can send this guy to other side. So you will have 121 plus U1, which is this value, the minus U4, which is 528.1, okay? Okay, we are like almost finished the problem. Here it is heat rejection because it's negative, right? We see it's negative, so heat rejection. Positive work, that means system is doing the work. So system losing two type of energy. One, the first thing, system is now expanding and doing the work itself. I'm not expanding, I'm not like compressing like as an output source. No, it's from gas, what who like which does the work. So you are losing the energy because of the work and because of release of the heat. So you have two things combined together. So this is why you have high change of internal energy between two points. Okay, so we finished. Just we will for part A we can plot. We can plot actually TS and PV diagrams. Okay, so let's say this is PV and let's say this is TS. Okay, let's put our points. Okay, so for PV I have three pressures, 100, 600 and 180, 18, 40, and three volume values, and here you have 2.06. okay, so let's put the points now. First point 100 and 0.85. okay, you are here. This is the first point. Okay, second point you have 600 here and your pressure, your specific volume is there. Okay, this is 2. 3, you have high pressure and same volume. You have like constant volume process. Then last 4 is you have going back to this pressure but with high specific volume. So this is the 4th one. Then you can use a color to just put your process line here, constant volume. Okay, I just put a little bit wrong place, but let's say like this. Then you have something like this. Then constant pressure. Okay, the process follows this path. We finished that. Now let's skip this and go to temperature entropy diagram. Put the temperature values. We have this one and 490. We have 720. Then we have high temperature. And what about entropy? We have 2 values only. Let's say this is 0, and I have high entropy, which is 0.92. Okay, so let's put the points. At the beginning, you have 0 entropy. You are here, and your temperature is here. Okay, from 1 to 2, you are doing an isentropic process. No entropy change. Okay, you are going to this point. So this is 1. This is 2. State 3, you are increasing your S, same as the temperature. So you are approaching this point 3, and again you have isentropic. You are like decreasing to this temperature, and entropy is same. Okay, so this is 4, and let's put our path. line, path curves. So here it's like this, then it's going to like this. Constant volume, constant entropy here, isentropic process. Here you have constant pressure. So you are following the isobaric line, isobaric curves, you can say. Okay, so this is the process diagram. These are the process diagrams. I can calculate the network easily. I know the work values for each point. Okay, so work net is just work from 1 to 2 plus work 2 to 3 plus work 3 to 4 plus work 4 to 1 when I come back to this point. So from 1 to 2, we have work done of like negative work because work input, this is work input, then plus 2 to 3, I have zero amount of work because it's a constant volume process. From 3 to 4, I have work output here, okay, because system is doing the work, then plus also I have another amount of work which is 121. This is also system's work. System is doing that work, so you can calculate the. Let me be sure about the signs here. P delta V, right? So this is a wrong thing we made. Yeah, let me just change the signs here. This must be the V1 minus V4. Okay, so this must be this is V1, so you don't have a negative sign there, so it should be like this. Then you get minus. Okay, because when it's minus, that means you have work done on the system, right? Not being done by the system. But let me be sure about it. So constant pressure heat rejection to initial state. Okay. It depends on the expansion or compression. Well, what's going on here? Let's see. From PV diagram, we can understand the work. Is it input or output? Here you are going to negative, like you are going to left, so this is negative work. Okay, 4 to 1 also negative work. Okay, because you are going back to, you are decreasing the volume here, decreasing the volume, so you will get a negative sign. Okay, so sorry for the mistake here. Okay, so you will get 414.7 kilojoule per kilogram. Okay, and what about other question? Calculate network output, determine the thermal efficiency. Thermal efficiency is just work net over Q in. So desired output over required input. This is our input, right? So 414.7 over Q in. Where is the Q input? From TS you can understand. You have here no heat exchange from 1 to 2, 3 to 4. You have only here. You can say here Q in, here Q out, right? So Q in just from 2 to 3. From 2 to 3, so it is 853.3. So this is the work heat input. 0.48, so you can say your efficiency is 48%. Okay, so we've calculated all values and we finished the problem. And you see that sometimes you can make a mistake, but you can double check yourself from the PS diagrams, okay? PV and TS diagrams, because TS diagrams will give you information about Q and PV will give you information about work, okay? So here, for example, no work because constant volume but you have 3 amount of works. Here negative work, here negative, you have negative work from 1 to 2. Here you have positive work because you are going to right, okay, when you're going to right and you have an area between the curves, so you have positive work. But here again, you are going, like you are compressing you are not expanding, you are compressing, right? So when you compress, so you have also negative work, okay? So that's all for now, and see you at the next video, and thank you for watching.